So, in this lesson, we are going to talk about linear springs. We are going to talk about linear springs. Why we are going to learn about linear springs, I will discuss in a minute. So, spring, you can categorize into two parts: linear spring, non-linear spring. We don't have non-linear springs in our syllabus, but I will show you what type of things you will get in non-linear springs. In linear springs, you get something like this. F is equal to Kx. I'm going to discuss this, but to find the difference between these two, I have to take this equation. The nonlinear spring is like F is equal to K1x squared plus K2x. It's a nonlinear spring. Now you can see by looking at the mathematical function, you will understand why the first one is called linear, second one is called nonlinear. You can see the quadratic behavior in the second one, x to the power 2. So the x to the power 2 is always nonlinear, you know that, right? So that is not in our syllabus. Now, if you think about the first one, F is the force and x is the displacement. So this is x to the power 1. So x to the power 1 means it is linear, right? Yeah. So when you go to university, you are going to learn about nonlinear springs. You do mechanical engineering. In the first day, you learn about nonlinear springs. So in a year time, you're going to have a big jump. Anyway, so let's try to think about a spring, linear spring, okay? So this spring, you can arrange in two different ways. You can arrange it in this way. You can fix it vertically. You can fix that horizontally. Right? So if you have a pure spring, then this length, we typically say L0. Obviously, this one also L0. So this length L0 is called rest length. L0 is called rest length. Then what I'm going to do, for this vertical system, I'm going to attach a ball. I'm going to attach a ball. So there will be a small stretch due to the weight of that ball. Right? Now think about a elastic band. When you attach something that goes down a little bit, right? Why? To balance the weight of the attachment. So this is L0. Due to this weight, mg, as I told you before, this is under gravity. Then there is a small extension. I would say that extension to be x0. Right? So that x0 extension is due to this attachment. Right? Okay. So now we will try to understand the physics behind it. Okay? Now, when it comes to this level, there are two levels here. So when it comes to the second level, this is called equilibrium situation. This is called equilibrium situation. Right? So at this equilibrium situation, this M mass is at a stationary position. Stationary position means that M mass is not moving, right? So at this situation, M mass is at stationary, not moving. So at the equilibrium situation, the mass is not moving. It just dropped down because of the weight, and that extension is x0, and then it comes to a equilibrium situation. Now, what researchers did, they tried to change the M and observe x0, right? So experiment is this. Experiment to find the relation between M versus x0. That means we have a genuine question. What if M is increasing? What is happening to x0 when M is increasing? Right? So we want to check what is happening to x0 when M is changing. M is increasing, X is increasing or decreasing. So they did an experiment to figure this out. So what they found when M is increasing, x0 is increasing. They found that when M is increasing, x0 is increasing. So this tells you that when M is increasing, W is increasing. W means a force, weight force. So when W is increasing, x0 is increasing. Correct? So this fundamental experiment they did. Okay. Now all of these are conceptual. You have to understand. Each and every word I can't document. Now, let's try to understand what is happening inside. Okay. Not. Now, suppose this is the equilibrium situation. Then this is x0. This is going to be mg. Now you have to understand. This x0 is because of this attachment mg, right? Actually, I need to change this one here. This is the equilibrium situation. This is the rest situation, right? Okay. So now what this mass is trying to do, this mass is trying to go back to this level. Reason? You remember, this was the rest mass. Because of this extra attachment, it goes down, right? So it came to a certain equilibrium, that's fine. But this spring, this part, always trying to go back to the rest level, right? So because of that, there is a force which is acting on this spring in the direction of the rest situation. And then that I'm going to say Fr, right? So this Fr force is building inside the material. Fr force is acting away from mg, away from mg. Fr tries to restore the spring. Fr tries to restore the spring. So this Fr is called restoring force. This Fr is called the restoring force. Right. Now, again, I'm going to drawing the same thing. So this is equilibrium situation. This is the ball. This force is Fr, restoring force. This extension is x0, isn't it? This x0 is the extension. Right. Now listen to this. This x0 extension is happening for what? This is happening with the spring, right? Spring is extended by x0. Now, this restoring force is acting on what object? Against spring. This mg is acting on which object? This mass. Right? Now, if you think about the spring, what are the things happening with the spring? If you think about this spring is stretching. So this stretch is associated with the spring. This restoring force also on the spring. So in this picture, these two are on the spring, not this one. Agree? This guy is on the mass here. Should be very clear, okay? Now, consider this linear spring. Consider this linear spring. Then you will see this Fr force is proportional to x0. This Fr force is proportional to x0. Now that means when Fr force is increasing, x0 is increasing. When Fr force is increasing, x0 is increasing. So how to increase Fr force? we can increase FR by increasing mass M, isn't it? So in the picture, when I increase the M force, when I increase the mg force by increasing M, FR also increasing, right? And X0 also increasing. Now, when you increase this force, this drag is improving. That means it will be like here. When you increase this mg, it goes further down. So when it goes further down, the restoring force also increasing. Why restoring force is increasing? Because that force has a lot of ground to cover to bring the system into this posture. So FR force should increase when the spring X0 length is increasing, isn't it? So all makes sense now, right? So we can increase FR by increasing mass M. Okay, done. Now, you can write this in this way, the relation. When mg is increasing, FR force is increasing. When FR force is increasing, X0 is increasing. Agree? Yeah. Now, I'm going to consider these two only. Why I'm going to consider these two only, you tell me? You listen to my explanation, you will understand. This FR and X0 both are acting on the spring. I told you that. FR is acting on the spring. X0 is the extension on that. Right? So that's why I'm going to consider this. Now let's go to math. In math, if you have F is proportional to A, you know Newton's second law. F is proportional to A means acceleration. Right? You can convert this proportionality to an equality. You can introduce the equal sign with a constant k here and put A. So this k is called proportionality constant. Proportionality constant. This is the math part. So that's how you make a proportionality into a equality, introducing a proportionality constant. Now, because of that reason, I'm going to say FR is equal to K times X0. This K is called the proportionality constant. Is called the proportionality constant. Also, this is called, this proportionality constant is named as spring constant. Spring constant. This constant is a material dependent property. Okay. So now, so far so good, right? I'm going to add something new here. Think about the directions. Think about the directions. Okay, let's think about this. Now, this is your equilibrium situation. Your FR is a force, which is a vector, right? Force is a vector. And this x0 is a displacement. So displacement and force are vector quantities. That means directions are there. Now you can see from this picture, direction of FR and x0 is opposite to each other. Right? Opposite to each other. Because of this reason, we are going to modify that equation. FR is equal to minus kx. FR is equal to minus kx. Now, if someone asks, why that minus? You should be able to tell the direction of x0 and the direction of FR are opposite to each other. So that's why you put that minus sign, because they are vectors too. Right? Now, if you want to find FR, if you want to find the magnitude of FR, if you want to find the magnitude of FR, what you do is you consider the mod value of FR. Mod value means the plus value. If you have a minus, you know that. So FR mod is equal to minus k x0 mod. Then when you have that, minus is ignored. Answer is k x0. So mod means the value only. So this relation F is equal to minus kx is called Hooke's law. Let's think about this. When the spring is horizontally placed, when the spring is horizontally placed. So let's think about that. So now what we are going to do, this is your rest length L0. We are going to pull this object from an external force. I'm going to pull that with external force, like I'm pulling you. What will happen? There will be extension here, x. There will be extension here, x. Due to this pulling, there is a restoring force on the spring. That is FR. There is a restoring force on the spring. Now, if you consider just the spring, if you consider just the spring, you will see that Fr is proportional to minus x, right? Minus x. Why that minus? Because of the direction. You can see directions are opposite to each other. You can see that, right? Then this inequality, you convert into a equality by introducing a proportionality constant, and that K is the spring constant. This K is the spring constant, right? So the same theory can be applied when the situation is in horizontal, right? All good. Now let's try to investigate about spring constant. Try to investigate about spring constant. So Fr is equal to Kx if I take the mod of Fr. So you can subject K, which is going to be Fr divided by X. Now, if you think about the SI units, force is given to you by Newton, X is given to you by meters. So this is going to be now Newton per meter. So K is given to you by Newton per meter, right? So that is how you find the spring constant.